Okay, so in the previous example then we had a beam between two supports, one of which was fixed in the vertical and horizontal direction, and one of which was a roller pin, so fixed in the vertical direction only, and we ended up with two reactions, well, three reactions in actual fact. We had a reaction the horizontal at this support, which was 0, and then under a load which we had at mid-span of P, where this was equal to L divided by 2, where the total length of the beam was L. We ended up with reaction forces of P divided by 2 and P divided by 2 at both A and B, where this was support A and this was support B. Supports A and B both had a pin connection to the support, so that they were not capable of generating any external moment reactions. So that we established by using the equations of static equilibrium. P divided by 2 were the reactions at each support, and overall the beam was in static equilibrium. That's to say, it wasn't moving up or down or left to right, and it wasn't rotating about any point within the plane. Okay, so in terms of structural design, when we come to design a beam like that, we need to know what the internal effects those external loads are having on the beam, and the principal effects that we consider are axial load, and because we have a rollered support at this end for a beam, of this beam in particular, there is no axial load. The horizontal reaction is 0, and there are no external loads which give a horizontal component. So the load P that's applied to that beam will give rise to shear forces and bending moments, and we need to know how to calculate those within the beam. And the way we do that is to split the beam at some point, and we'll split it at some point here between the support A and the application of the load P at mid-span, so some point between those we will consider, and that gives us a free body. So this body, which has a reaction of P divided by 2 at this location, needs to provide a set of reactions, internal reactions, which counteract that. So we have a force which we call a shear force, and a bending moment diagram which resists the bending moment due to P2 multiplied by the distance from the point at which we are considering, and we will call that x, as it's in the x direction. Okay, so in terms of static equilibrium, our equations of static equilibrium for this free body, we know that we have a force of P divided by 2 acting upwards as a reaction, and that gives rise to internal forces which need to counterbalance what's going on there. So we have an internal shear force initially, and by the principle of sigma, so the sum of all the forces in the y direction, if you remember, we chose for this particular problem y to be vertical, x to be horizontal, and z to be out of the page, or out of the screen. So the sum of the forces in the y direction, so the sum of the vertical forces, the shear force, which we will call V, and the internal bending moment we will call M at X, okay, and V at X. So for our internal forces, or our forces in the system, all the forces in the vertical direction going positively upwards minus those coming downwards, the shear force have got to equal 0. Again, that's from our principles of static equilibrium. For this to be in static equilibrium, this force at the reaction has to be balanced by an internal shear force, which is equal and opposite. So we say that P divided by 2, which is in the positive direction, minus V is equal to 0, therefore V equals P divided by 2. So we can begin to draw our shear force diagram for this beam. So at any point where P upon 2 is applied, so that's at any point along this beam, as we move along this beam until we get to the point at which P comes down, starts to act, then we have just this shear force of P divided by 2. So we say that the shear force in that part of the beam up into its midspan is given by this diagram, where that is equal to P divided by 2. When we get to the point in the beam where we are exactly halfway along, we are subject to a P in that direction, and we've just come slightly to the right hand side of that, so we've just picked up that P, and we still have the reaction at A, which is P divided by 2. So we say that our shear force here, if we sum in the y direction, the vector forces in the y direction, P divided by 2, and this time minus the full amount of P, and then we are trying to find a shear force, and in actual fact the shear force, we will see, let's draw it the same way we had it above, shear force Vx, where we've got an x which is greater than L divided by 2, so that was less than L divided by 2. We now have a situation where we've got x which is just slightly greater than L divided by 2. So that's L divided by 2, and we're looking just slightly to the right of that now. So we get a sum of the forces in the y direction. So P divided by 2, which is this reaction, and then minus P, and then is equal to our V. Okay, so our P divided by 2 minus P is minus P divided by 2 is our shear force at that point. So we can then say that at the midspan of this, where the beam, this point is L divided by 2, length divided by 2, we find that the shear force suddenly changes with the application of that P load now to go to minus P divided by 2, and indeed as we carry on at any point within this part of the beam here, that will continue as being P divided by 2 minus P, which gives us a shear force of minus P divided by 2 right the way along until we get to this point here where the shear force is P divided by 2 minus P plus P divided by 2, so it comes back up to 0 at the support B. So that's A, that's B, and we have, just for completeness, our point load at midspan at L upon 2. So this is now our shear force diagram, which goes to positive P divided by 2 and then negative P divided by 2. And it flips over at the application of this load P at midspan. The selection of the shear force, what's positive and what's negative, is again depending on how you want to look at it. We look at it as though we are working in this direction. So if we, for completeness, if we look along the beam in that direction, then that gives us the difference between a positive and negative shear force. But for example, at this point here, we end up with a shear force. So within the beam, if we split the beam and separate it, those are equal and opposite. So we end up with a shear force in that direction and a shear force in that direction to counterbalance these reactions at these points here. Okay. In the next video, we will look at the internal bending moments within that beam.